Consider the matrix A equals 1, 4, 2, negative 1. Suppose V was an eigenvector of this matrix with eigenvalue lambda. What must be true? We've seen the definition in a previous video would mean that AV needs to equal lambda V. But how can we actually figure out what V and lambda are? Let's suppose that V was a vector in R2, let's just let it equal xy. So what does AV look like? That would look like 1, 4 to negative 1 times xy. Okay, and so that equals x plus 4y and 2x minus y. And if we want that to equal lambda v, then this would imply that x plus 4y 2x minus y needs to equal lambda times xy. But this would imply that x plus 4y needs to equal lambda x, and 2x minus y needs to equal lambda y. But if we move everything to one side, then this all implies that x minus lambda x plus 4y equals 0, and 2x minus y minus lambda y equals 0. Give myself a little space. Let's move back up here. So this leads to the fact that if I kind of factor out and rewrite this, that 1 minus lambda times x plus 4y equals 0, and 2x plus minus 1 minus lambda times y equals 0. But what does this actually tell us? Well, it tells us that xy, this vector v, would be a solution to the matrix equation where I've got the coefficient matrix 1 minus lambda, 4, 2, minus 1 minus lambda times our vector v equals the 0 vector. So let's actually explore this matrix a little bit further. What you might notice is that it is similar to our original matrix A, actually. In fact, the 4 and the 2 are still there in their same positions, the 4 and the 2, the 4 and the 2. And we've also got the 1 and the minus 1. Here's the 1 and the minus 1, but we are subtracting lambda from each of those terms. So we are taking sort of our original matrix A, and we are subtracting lambda from the diagonal. And so one way we can represent that using matrices is to take A and subtract lambda times the 2 by 2 identity. So this would be A minus lambda times 1, 0, 0, 1, which is A minus lambda 0, 0, lambda. So A minus lambda I, if we do A minus lambda I, we end up getting this matrix down here, this 1 minus lambda 4, 2, and then minus 1 minus lambda. And so V would be an eigenvector of A if it is a solution to this particular equation, which is a homogeneous equation. And let's write this out. So what we're kind of discovering here is that V, if V is an eigenvector of A, then A minus lambda I times V would be 0. So V is a solution to this homogeneous equation, and in particular, it needs to be a non-zero solution. Our eigenvectors shouldn't be the 0 vector. So, we're looking for, so we are looking for non-zero solutions to the equation A minus lambda I V equals the zero vector. And what we've studied in a previous section is the fact that this particular homogeneous equation will only have non-zero solutions if that matrix, which in this case is A minus lambda I, is non-invertible and would therefore have determinant equal to 0. So this is only going to be possible. Back up here, give ourselves more space again. So this is only going to be possible. This is only possible when the determinant of A minus lambda I is equal to 0. Because then A minus lambda I itself will not be invertible, and that particular equation, A minus lambda I V equals 0, will have infinitely many solutions, which is what we need because we know it automatically has the one solution V equals 0. We want a non-zero solution to that. So let's actually now apply that to this particular example. If we look at the determinant of A minus lambda I for this example and set it equal to 0, we're going to be looking at the determinant of the matrix 1 minus lambda 4, 2 minus 1 minus lambda, which is going to be that AD minus BC. So it's going to be 1 minus lambda times minus 1 minus lambda minus 8. And we want this to equal 0. Let's clean this up a little bit. So if we expand this term out, we'll get a lambda squared. And then I guess a plus lambda and a minus lambda. So those middle lambda terms will cancel, and a minus 1 and then a minus 8. So this becomes lambda squared minus 9. So we're looking for lambda values such that lambda squared minus 9 equals 0. We can solve this pretty easily to get lambda would be plus or minus 3. So apparently, we will only have an eigenvector v if we have an eigenvalue of either 3 or negative 3. What would an eigenvector v then therefore be equal to? Let's take lambda equals 3 to begin with. So if lambda equals 3, then an eigenvector v will be a non-zero solution to the equation a minus 3i equals the zero vector. So let's take a look. So if lambda equals 3, let's consider a minus 3i times v equals the zero vector. So that's going to be, I guess, a would be, a minus 3i would be 1 minus 3. Just do all the work here. 4, 2 minus 1 minus 3 times v equals the zero vector. So we're looking then to solve the homogeneous equation with augmented matrix -2, 4, 2, -4. And then we'll put 0, 0 over there. And we can row reduce this and use either a calculator. Actually, this one's not so bad. You'll notice that our two rows are equivalent to each other. And that's hopefully not too much of a surprise because we were looking for a lambda value where the determinant of a minus lambda I was 0. And therefore, we sort of knew if we've plugged in a lambda value there, such that the determinant was 0, that these two rows would have to be scalar multiples of each other when we have a 2 by 2 matrix like this. So this would row reduce to 1, -2, 0, 0, 0, 0. So as long as, again, if v is sort of x, y, as long as, I guess, x equals 2y, and y can be anything we want, y would be a free variable here, then we get an eigenvector. So for example, we could let v equal, I guess if y was 1, then x could be 2. So 2, 1 is apparently an eigenvector. maybe I'll come up where I have a little blank space. Let's check that 2, 1 works. So is an eigenvector. Okay, so if we do A times 2, 1, 1, 4, 2, negative 1, times 2, 1, we get 2 plus 4 is 6, 4 minus 1 is 3. So we do get 3 times 2, 1. So it worked, hooray! We could play the same game with negative 3, and we would get an eigenvector there. And actually what we see is that we don't just get an eigenvector here, we get this relationship to tell us sort of what our eigenvectors have to satisfy, but we can get infinitely many eigenvectors from this. So instead of y equals 1, we could let y equal 2, or y equals 10, or y equals 0.5, or negative 2, right? Anything we want, we could get the x, and that should be an eigenvector, and we could check all of those. So what did we do here? Recall that an eigenvector v with eigenvalue lambda satisfies AV equals lambda v. So if AV equals lambda v, then we can subtract that lambda v from both sides. So we'd have AV minus lambda v equals the zero vector, which we might write as AV minus lambda IV equals the zero vector. And then we can look at A minus lambda I times V equals the zero vector. So this is sort of the homogeneous equation, right? So this is that homogeneous equation that we're looking for non-zero solutions to. So an eigenvector is a non-zero solution of A minus lambda IV equals the zero vector. So the matrix A minus lambda I must have a non-trivial solution. So what does that tell us about A minus lambda I? It means that the determinant of A minus lambda I must equal 0, because A minus lambda I must not be invertible. And this equation is called the characteristic equation of A. The expression determinant of A minus lambda I is a polynomial in lambda. If we go all the way back to this big mess of work, I'll highlight it here, the step where we ended up with the determinant of A minus lambda I for this big example ended up to be lambda squared minus 9. So notice that's a quadratic polynomial in the variable lambda, and we set that equal to 0. So this polynomial is called the characteristic polynomial of A. If A is a 2 by 2 matrix, then that is a degree 2 polynomial, quadratic. If it's a 3 by 3 matrix, then that determinant of A minus lambda I is a degree 3 polynomial, or cubic. And in general, if A is an n by n matrix, then the determinant of A minus lambda I is a polynomial of degree n. Its roots are precisely the eigenvalues of A. So the eigenvalues of A will be solutions to, so roots, just to remind you what that means. So these are solutions to determinant of A minus lambda I equals 0. So we've turned this, somewhat complicated original question of, can we, given this n by n matrix, can we find vectors such that AV equals lambda v? We've turned this into a purely sort of algebraic question. Can we find roots of this degree n polynomial? And that's not to say we've really, made it much simpler necessarily, because if you kind of go back to whenever you were playing around with polynomials in an algebra class a long time ago, just like a standard algebra, not a linear algebra class, right? Maybe you solved some of these kinds of equations where if it was a quadratic, maybe you did some factoring or used the quadratic formula. So those are not so bad, although that can get kind of ugly itself. And then, cubics, even the cubic case, you might sort of be left with doing some guess and check and then some polynomial long division if you ever did any of that, right? So, and then, fourth degree or fifth degree gets even more complicated. So I don't want to sort of say that, okay, well, all we're doing now is finding, the roots of, or the solutions to this polynomial equation, and make it seem like, okay, this algebraically is much easier, but it is kind of interesting, and maybe it is a bit easier but still kind of complicated. But it is, I think an interesting thing we've done. We've turned this sort of really theoretical, complicated thing, and we've used a lot of the tools that we've seen this semester. So I think what's really neat is, here we are in chapter 4, towards the end of our course, and we're bringing together determinants and this homogeneous equation and the geometry idea, AV equals lambda v, sort of motivating eigenvalues and eigenvectors, and kind of we're going to see the connections to matrix multiplication and stochastic matrices. So this is sort of a big culmination of a lot of the things we've done, this big complicated problem, and we've kind of boiled it down, at least to begin with here, and we'll see some examples. We've boiled it down to a problem we may have seen many moons ago in an algebra or an algebra 2 class, where we're just sort of, okay, here's a polynomial, can you find me the roots? So sort of an interesting thing that's going on here. So we're going to see in future videos plenty of examples of, can we do this and how this can be complicated, and maybe some technology that could potentially help us out here. But just to sort of get us started here with some of the algebra, and sort of see where we're going, we have this characteristic polynomial, really, really important object we've introduced.